As you recall, so we've now quite extensively discussed planning, analysis. There's some other phases still to discuss, but we will go through them much briefer. Why? Because they're more for people with a technical background, more technology oriented. But nevertheless, it's important for you to know what it is about, without being able to perform the task yourself. First, want to discuss the design phase. After you have the planning and the analysis, design needs to happen. It's basically the same as if you would design a car. Then the analysis can be, well, let's make sure that the car is able to go up to 120 kilometers an hour. Let's make sure that in certain angles of a curve that you're driving, that the car stays nicely on the highway and doesn't crash. Make sure that we can go forward and can go backward, that we have some lights there. This is the analysis. The design is how do we realize that? And that is also not straightforward, because what does an engineer do, and what also needs to happen from a software point of view, is you need to consider all those requirements and to go from what is called functionalities of the system, to the construction. And this is not just taking one requirement, one component, one other requirement, one component. Because suppose again that we would look at the idea of a car. If one of the requirements is we should be able to drive forward and we should be able to drive backwards, most cars these days are able to do that. Well, if you would take them one by one, it would imply, okay, we need something to go forward with our car, so we need an engine, right? We need to go backward as well, so we need another engine. Or if we say, well, it needs to be safe, it needs to be balanced on the road, and we need to make sure that it does not that it does not crash. What would be the one component that is making sure that our car is safe? No, that's something that the whole car needs to be designed such a way that the weighting is correct, that the aerodynamics are correct, and going forward and backward, well, we can basically realize that by having one engine. That one engine will allow us to go both forwards and backwards. So analysis, having all the requirements, and then going to a design is not straightforward. That's an engineering activity, and that needs to happen for a house, for a car, also for IT systems. And so this activity will be about what is the overall architecture, what are the building blocks that we need, what are the modules, often as we discussed before, what are the modules, the different function, how will we realize those different functionalities, how will we connect them internally, how will we connect them externally via interfaces, what kind of technologies will we use. And as I said before, this is not a simple one-to-one mapping. This is actually some kind of creativity is involved in that. Some kind of expertise, technical expertise is required to take all those requirements and to say, how are we going to realize that? If certain algorithms are required, like suppose that we are making to routing software to go from location A to location B, well, the algorithm that you use to make sure that you take the shortest route or the most efficient route or whatever, that kind of algorithm is also part of this design phase. If you want to sort certain numbers, or if you want to apply a certain method algorithm, in most cases, the actual design of that algorithm will also be part of the design. So in the analysis, we had the business case with all its components. In the planning, we had the business case with all its components. In the analysis, we had the data models and the process models and the use cases. And here, as outcomes, as artifacts, we have again the data models, process models, but enriched with technical data. So they will make sure that the databases are adequately represented, the interaction with other systems, and so on. So some of those models that you might produce in the analysis phase might be the starting point for those models in the design. This is something that we will not cover in this course because it goes a bit too technical. After the design, in a linear way of going through the project, we come into the implementation. And it's only at that stage, only in the fourth phase, that we actually start creating something tangible, so to speak. So in this case, software. It's only in this phase that what we need will be created into something which works, into software in this case. So the artifact, the outcome that is created in this phase is the source code, the lines of code that are there in software program, as we said in the first lecture, those statements in kind of computer language, to put it simplistically, those statements, they are created and they are programmed in that phase. Several ways to do that. You could have in-house programs, you could hire external people, consultants. You could have external companies doing that for you, having outsourcing. Or, as we said before, probably at the end of the analysis phase, when you make the analysis of your processes, when you make an indexation of all the requirements that you have, it might be the case that you say, well, our processes are close enough to an existing off-the-shelf application, or we are willing to adapt our processes so that they closely align to an application that already exists, except for those processes which provide us a competitive advantage. So we might not be doing all the programming ourselves. We will take an existing application and we will then do the parameterization, the configuration, and sometimes also the customization of that source code that already exists. So in this case, it's source code which is adapted a little bit. So that means at the end of the implementation phase, we have source code that's runnable, that can be executed. The actual running or the actual usage of it starts during the testing. So in the testing, we're going to see, okay, we have created something. What happens if we use it? So it should be tested in that phase, whether what we have created, the software application, whether that matches what we wanted, the requirements. Now, there are different ways to do that. In general, these are 4 types of tests that are generally used. So we have the validation, and the validation will check the application that we have. Does it meet the actual needs of the organization? Was the right application built? The verification is more targeted to the question, does the application work towards the requirements that were formulated in the analysis phase? Why is this different, and why is it important to make that distinction? Anybody having a clue? So here we check, does the application meet the actual needs of the end users? Here we check, does the application work according to the requirements that were put forward in the analysis? Sorry, it might be due to the standard securities, yes. Yeah, that we thought of. Yes, indeed. And so why is this relevant? Because what the application, or sorry, what organizations, what the end users need at the moment that we are testing the application, might not necessarily be the same thing as formulated during the requirements phase. Might be for several reasons. Either the analysts, they didn't do a very good job, so they missed certain things, or they did not accurately represent them, or there might be an issue with the fact that, okay, maybe the project had a very long throughput time, a very long time spent to become realized, and maybe the analysts did a perfect job, but they made their analysis 2 years ago, and now customers or the end users, well, they have changed their behavior, the organization has changed, the market has changed. So these are 2 fundamentally different questions. Of course, you want this, but your developers, your consultants who are designing the application, well, normally you can only take them accountable for this because they get requirements and they are required to provide something that works based on the requirements that you provide to them. Yeah. So these are, I mean, of course you want this, but there might be a difference in reality. Now, when we look at a system, often we will not just use the system as a whole. Often some unit tests will be done, so specific parts, specific modules in the system will be checked. So does this part of the system work? Does this part of the system work? Does this part of the system work? And then there will be system tests, those who check the links between those modules. Do they accurately communicate with one another? Do they interact in a proper way? And of course, there are also some security application controls. So testing whether we can only verify or whether we can only process the authorized data in a complete and precise way. To check whether, for instance, also if data is authorized to be processed, whether the input, the output, and the throughput and output is done correctly. So can we process the input data? If yes, is it delivered in the right format? Are any calculations that need to be performed correctly? And the data, is that then also, for instance, correctly represented? So on different dimensions, on different areas, tests will need to happen. And this is actually an area where you as users or as managers also need to be heavily involved in. One of the reasons, again, why projects fail is also because there might be intermediate versions. There might be already, before the final product is there might be prototypes. Then there are normally testing sessions, and some of the testing will be technical, but some of the testing needs to happen with end users. And then, of course, it's important that those prospective end users that are very much involved, that they are actually testing it, that they show up, that they dedicate time, that they dedicate resources to do it, and that they give honest feedback. If something is not working, if something is not according to your needs, that is the time to mention it, because then maybe something can still be done. If you wait until the whole product is delivered and then end users start saying, but we would like to have this and this and this adapted, while they could have said that earlier during the test, then of course you hamper the successful completion of that project significantly. So what is the outcome? What are the artifacts here? Well, testing plans. So you need to have some scripts, and ideally these should be actually already designed during the analysis phase. So what is the behavior that we want? And we will also execute them. So we will check, is the behavior that the system shows, is it according to what we want, to what we planned, yes or no? And if not, maybe still some adaptations need to happen. Once we have done that, we have an application that should be working. We have tested it, it passed the test. Then we should go live, go into production, as it is said. Different ways to do that. You can have a big bang approach, as it's called, where you basically say there's a time before and there's a time after. So at some point in time, at a certain day, we will say, as of now, the system runs, it's in production, and all users need to use it. If you have a system that is there to get reimbursements for your traveling costs, well, until yesterday, you could use the old system. As of today, you use the new system for everyone, everywhere in the company. That's of course riskful, because if you do it in one go, a lot of things might go wrong. There might still be things that have not been captured by the testing. Suddenly the system cannot cope with the full load, everyone exiting it at once and so on. People don't understand it, people not being trained and so on. So a possible mitigation is a fallback scenario where you say, well, okay, we try the new system as of today, but suppose that significant things go wrong, then we still have the old system as a backup to kick in if needed. Another way to work is with what's called a parallel strategy, where you will go for the new one and the old one to run in parallel during a certain period of time. Of course, that's much less risky than the Big Bang approach in terms of functionality. You make sure that you have the old system and then you have the new system, so something will work in any case, but of course it's more expensive. Also, what happens here is that people, you also have some, you always have some first adopters, some technologically savvy and enthusiastic people, and they will be encouraged and they will be motivated to use a new application. But that's only 5 to 10% of your users. Most users, if you provide this strategy, they will keep on using the old system until you say, well, now it's the end of the parallel strategy, guys. You have all had the opportunity to test both systems. We will phase out the old one, so you will not be able to use it anymore, and we will only rely on the new one. Then basically this is kind of a postponed Big Bang strategy. and because you want that people start using it. So if you go for that, well, it sounds good, but then of course you need to do some user management and to make sure that people are actually also using the new system, so that you can counter any drawbacks. Other alternatives are, for instance, a pilot study where you say, well, let's choose one division, one department, one team in our organization, which is maybe, again, a bit more technologically savvy, which is motivated, who wants to test it out and gives us already feedback so we can adapt accordingly. Or we can say, well, let's do it in a gradual way. So everyone starts using it, but only for a few initial functionalities, and once that works, we go to the next functionality and to the next functionality. But of course, also that has a drawback in the sense that in that case, you also have two applications running at the same time, covering parts of the needs that you want. So some needs will be fulfilled by the old system, some needs will be fulfilled by the new system. And that means that you need to be interfacing between those two things. On PowerPoint, always very nice. In reality, super difficult. Making interfaces between systems, making sure that they work, making sure that they keep on working when things change in one of both applications is super, super difficult. So it's an option, but it's not straightforward. Nevertheless, you need to choose one of them or a combination of them. But I think it's relevant to know them and to know the pros and the cons of each of them. What is the delivered artifact? The outcome of this phase? Well, it's software that has been implemented, that has been tested, and now it's actually also it's working. It's in production in your company. And then most people say, well, it's done. And no, unfortunately, it's not done. We have one final phase, which is super crucial. And some people say, okay, this is the project. And that's true. The project development ends here. But the actual usage continues and requires maintenance. So once software is there, it requires maintenance. Basically like a house, it also requires maintenance. If you have a leakage somewhere, then you need to fix it. It's the same with software. You need to make sure that you put continuously money into it to keep it up and running. And although it's intangible, that you cannot feel it, that you cannot always see it, it is needed, it is required. Also there are some well-known categories of maintenance that are typically distinguished. The most known one is corrective. Corrective maintenance is the one where you have an error, a bug, the blue screen that happens. Well, then you need to make a fix. Some could be emergency fixes that you say, okay, we make a hot fix. It needs to happen immediately because something happens and it prevents the normal functioning of the basic functionalities of the program, so we need to fix it. But you also have other ways or other types of maintenance. You could, for instance, go for perfective maintenance, where you say, well, we have an application here, but as people are using it and are hopefully glad with it or satisfied with it, we add some new functionalities to it. So we make it better, we make it more encompassing, or it runs already, but we make sure that it goes even quicker, more efficient, higher performance. Those two this is most commonly what people associate with maintenance. This is something that they often also can imagine and that they agree with. Those two are less well known and nevertheless very crucial as well. First one here is adaptive maintenance. Adaptive maintenance is the one that you often cannot see, but it is required in the sense that new versions might come from your hardware, from the software systems, the platforms, the underlying platforms that you use, the operating systems, the database management systems, and so on. They might be updated, and they require often your own software to be updated as well. It's, again, making the analogy with a car, could be that suddenly the type of road that you're driving on, and they require your tires to be thicker because the substance of the soil of the ground changes. Well, that means that you also will need to adapt the design of your car. That's the same with software. You need to, if a browser comes up with a new version, you need to be able to make sure that your software still is still accessible with that new browser. And so these are external events. You don't have them under control. And if you're lucky, you followed all the standards and whatever, and so then it will be more or less okay. But in some cases, it will really trigger you to do fundamental changes. That's difficult to defend in a business case, because what will you get? You will get nothing in addition. Here, you know, okay, the bug is fixed. Before that, we couldn't do something. Now we can do something. So we progress. We want to invest money. Perfective, we have more functionality, so you want to pay for it. Easily defendable. Adaptive one, very difficult to defend, although it's strictly necessary. And it's a continuous cost. It will happen for the whole duration of the usage of the software system. Other technologies evolve, and you need to follow. Preventive is even more difficult to defend, and also this is a very relevant one and a very important one to actually carry out, and it's called preventive. What we see is that when software applications are built, they grow more and more and more complex over time. People write the code, and in the beginning it's all very neat and structured, and after a while, okay, a hotfix needs to happen here and a quick fix needs to happen there. And so sometimes it's very strict in terms of deadline, and it needs to happen quickly, and some dirty fixes need to happen. And it works on the short term, but in the long term, you need to make sure that your code is well structured, that it's well documented, that it works fine. Preventive is that kind of maintenance that will say, well, we're not going to change any bugs, any functionalities. We will not even make it more easy to work with the new technology. We will prepare the software. We will restructure the code so that later on, when these changes come or when a bug pops up, that we are more easily able to detect where the error is, to check it, to fix it, and to make sure that it's easily readable. Also, that's very difficult to defend often in management meetings, but very relevant. So yeah, I would also advise you really to be aware of this. This is normal in IT projects, as show. It's normal that money needs to be spent on that. Artifact here is, we had software. The software was already implemented, was tested. Here, during the maintenance, it's revised, it's updated. I want again here to refer to this idea of the total cost of ownership that I mentioned in the first lecture. Well, the total cost of ownership is that idea that says, well, if you look at an IT project, you don't only look at the planning to the go live, but you look to go live and the maintenance. So it's a total cost of ownership. As long as you own the application, as long as you run it, you need to be aware of the costs. And so all these types of maintenance, they are a big part of that total cost of ownership. There are not too many studies on the cost structures of IT projects. Some of them do exist, and one of the more recent ones, but it's almost already 20 years old, but still, nevertheless, I think these days they're still relevant or still in the same magnitude of order. It can be 50% or more of the costs that are really dedicated to maintenance. And so it's important, and it's also not tiny or small. Again, to make this point stronger, I want to highlight two phenomena or two concepts to you in the context of this maintenance. The first one is what's called the law of increasing complexity. There are not too many laws in computer science. It's called a science, but actually we still don't have too many laws. One of the laws that has also been here and there empirically tested is the complexity or the increasing complexity of a software. And it's basically what I said already before, more or less, that is, it's a phenomenon that as an evolving program is continually changed, its complexity, deteriorating structure, increases unless work is done to maintain or reduce that complexity. And that's something that is observed in almost all IT projects. The older the code becomes, the more complex and the less structured it is. So the more likely it is that you introduce bugs, the more difficult it becomes to fix, the more difficult it becomes to integrate new functionalities. So what is there to keep in mind? Well, it's a typical thing that happens in IT projects. The longer the project lives, the more complex, the more costly. It also stresses the fact that you need to think upfront in the design phase well enough what are the building blocks? How are we going to structure our application so that later on, hopefully, that structure deteriorates less quickly, as well as it defends that reason for preventive maintenance, that you know that code typically degenerates over time, so it's worthwhile to invest even before that complexity arises, and to really strike it down. Sometimes people use this idea of technical debt or technological debt, which is very much related to this. You have a history of your project, you have a history of the source code and so on, and if that's done in a quick and dirty way, that's a kind of debt that you carry on, because it will create additional costs if you do not fix them in the beginning. And also in terms of this IT productivity paradox, this is a very, very interesting to think about it. How can it happen that as a program evolves, that it becomes ever more complex and ever more difficult to maintain? Well, that means probably also that you need to increase the maintenance costs associated with that. Might be part of that IT paradox. Yeah, you invest a lot of money in it, and maybe you don't get so much more effective or efficient. Same here, the idea of combinatorial effect, which was also coined in the context of maintenance, that changed, or that says basically that what happens often in software is that the impact to implement a certain change, the effort that you need to do to implement a certain change, a bug, an additional feature, and so on, that impact is not only dependent on the type of change. So I want to print something, or I want to send a message, or I want to have a nice graph. So it's not only you can imagine that a graph with 20 components is more costly than a graph with one component. So that's the type. That makes sense. If you have a more complex graph, that you pay more. But this statement says, well, it's not only dependent on the complexity of the requirement that you have. It's not only dependent on what you ask. It's also dependent on the size of your system. So if you want to generate a certain graph, it will, in most cases, be more easy to do in a small system than in a big system. So you might have two different systems, same requirement that you apply to it, and in one system it will be easier than the other one because the easier system is smaller, is less older. And we know that systems, they always grow. There are almost no systems that will become smaller over time. So if you then make the full reasoning and you know a system typically grows over time, as it grows over time and it gets older, its structure deteriorates, becomes more complex, and it becomes ever more complex and difficult to perform changes to that system. And the effort, the cost of performing a change is then not only dependent on the size or on the type of change, but also on the size of your system. So these are interesting concepts to think about when you think about maintenance, because these things happen all the time when you're managing software projects. To end with some, as we said, with the enterprise applications, we had some managerial reflections, challenges. We will also have some brief challenges here, or some reflections, I must say here. First of all, project management, IT project management, there are some definitions you need to be aware of. Most of the time, people only talk about on a project or an IT project when it is something non-routine, it's something unique. You have a start, you have an end, you have a clear goal. And so it's not something that you do every day. It's something unique. You create an ERP package, you create a supply chain management system, you create something for your customer management. It's something unique. When you manage such a project, people often talk about this project management triangle, meaning time, cost, and quality. In the ideal world, your project is managed in a sense that you realize all the quality, all the functionalities required, that you do it on time and within costs. In a lot of cases, you are not able to fully balance on the triangle, and you might go over time, over budget, or not realize everything that is required. But then in a lot of cases, there's some kind of emphasis that you might place. In some cases, time is essential. If you want to be the first mover in an industry, you want to have the first mover competitive advantage, then maybe it's not so problematic if you go a bit over your costs, your envisioned costs, or if you do not provide all the functionalities initially required. No, you just make sure that you're on time. Likewise, if you're in a nuclear plant, probably you think it's more important that the quality, the safety of your software is 100% okay, and if it then goes over cost over time, less problematic. If you really want to be super efficient and don't want to make too much cost, you don't mind so much it goes over time or that not all functionalities are provided, but you do care about the fact that the budget should be very low. So depending on the context, depending on the project, you might reshuffle some priorities there. Now, as I said in the very beginning, the way how we went through the phases was in a very linear way. First planning, then analysis, then design, then implementation, and so on. That's what's called in literature and in practice, it's the waterfall approach. You go from beginning till the end, it's one sequence, and when you have completed the planning, you sign off, you go to the analysis, you complete the analysis, you sign off, you go to the design, and so on. It still happens that projects are executed in this way, but it's a minority. It can have its benefits when you're really having very complex, very large projects, and when you know that the requirements are very stable and well known, then you can go for that. But there are also some important drawbacks. As I said before, and as we saw the difference between verification and validation, there might be projects that take a long time, and so the time from which the requirements were documented and the time at which the application is actually put into production when it went live, there might be some time spent there. And of course, the world changes, people change, businesses change, and so the requirements that were put on paper at that time might not be the requirements that we have today. So there might already, due to the time spent, be a problem. It also facilitates a lot of the throw over the wall phenomenon, which is known in that world as the fact that people feel very safe when they create something, they finalize it, and they say, okay, the analysis is over. We don't care about the design and implementation anymore. We have done our job. We've put on paper, you guys, you should do this, and the other ones should take care of it. Whereas actually you want involvement of certain stakeholders throughout the whole project. You want that they are informed. If something cannot be realized, is there an alternative? You want to have you want to make sure that everyone understands very well what you've written in terms of requirement. So also that throwing over the wall phenomenon is a risk. What equally happens in this setup of a project is that the first time that an application is validated is only after the project has been delivered. So there might be a big time gap. It might really deviate from what you want, from what you imagined. And also from a management point of view, it's quite tricky. Yeah? You're investing millions and years and a lot of resources into something, and you only see the very first usable result after years. That often feels very uncomfortable for people investing money. And so in some cases, it can still be useful, but in a lot of cases, it's also very costly, inflexible, and time-consuming. So what we see that often happens in reality is iterative modeling, and you will see that depending on the year or the phase that we're in, people will use other terms. They will say, we're working agile, or we're working with DevOps, or we're doing continuous integration, continuous development. And of course, all those approaches, they have their own emphasis and their own way of working. But again, this is not a software development course. It's important for you to know that you have this big distinction. You have the waterfall approach, purely linear, and then you have iterative approaches, where people say, well, we will not go through all the phases of the software system development lifecycle once. We will go through them several times. We will first develop this part, then this part, and then this part in a more iterative way. Some of the benefits here is that people can use prototypes. They can use already a first version, or they can present you a first version of the program before the real end of the project. It can be something that is to throw away. So they show you the interface to validate the requirements or to show what they have right now, or it could be an evolutionary prototype, as they call it. So it's something that's there, and they say, well, it's not all functioning yet. Those buttons don't work. These calculations still don't work, but this part does work. We have implemented it now. Give us your feedback. So you already have preliminary versions of parts of the system along the way. So that means that you have the opportunity to involve end users throughout the whole cycle, not only in the beginning, but also intermediate checks are possible. And you're not investing years and years and years of money without knowing what you're doing. No, you have intermediate points where you see, okay, now this is being realized. Now this is being realized. Okay, we're doing quite well. It also allows you to do some risk management. You could decide to focus first on some elements which are more risky and then only to do other risks. So you try to eliminate some risks and not to risk all the money that you invested until the end when the really risky thing is being done. And you could, of course, also even have intermediate releases that you say, well, we actually we can already release parts of the software and actually use them in practice before the project has been finalized. The drawback then here is that, of course, you need a little bit more of coordination. It's not just one planning, one analysis, and so on. You need people who take consideration of all different iterations that there are, different teams that are often created to make sure that all those sprints, all those parts of development process, that they're well tested, that they are well carried out, and that you follow that up. Yeah. Okay. As I said before, I typically tend to say, okay, the two big strengths, you have the waterfall approach, you have the agile approach. You will see that in practice and in literature, there are several approaches that use different terms to say something similar. For instance, here we have the iterative model from VUB, which basically is the same as iterative, or goes not the same, but it goes along the same ideas and philosophy with a specific focus on risk management and reduction. So this methodology says we go through evaluation of risks, to development, to testing, and to the next phases several times, but we tackle those items which are most riskfully first. Or you have the RUP process, the Rational Unified Process, which you see here, defined by Kroll and Kruchten, who say, yeah, you can have, you see here the different phases more or less that we discussed, but they are not so linear. You have an inception phase, an elaboration phase, a construction and transition phase, and you see that modeling requirements, for instance, okay, of course, it has a peak in the beginning of your project, but it does not just end at a certain point. It keeps on happening a little bit throughout the whole project, but the intensity and the amount of resources that you devote to it, it decreases a little bit over time. And the same is true for implementation then. Okay, in the beginning, there's almost nothing, but there in the later phases of the project, it significantly increases until the end, it goes down a little bit more. Yeah? So there are many different approaches, but they all tackle that same question: do we go linear, one phase after the other? Once one is completed, we never go back, or do we go more iteratively? Yeah. Then there's one final approach that you might also come across, which is called end user development, where we do not go through all those phases that we just saw, neither linear, neither iterative. We just have end users themselves who say, well, I can do it myself. Today, we see that there are some tools which allow people to do that. For instance, they take their Excel sheets and they start doing some small programming themselves, formulas, Visual Basic, whatever. Scripts, they enter them and they put them there. You even have people who will use SQL, which we will also see in one of the sessions, the basics of that, who use that to do certain calculations, do certain derivations. And so having those tools, using those tools is very interesting for end users, but we should be careful not to make them into permanent applications. Because, of course, it has clear advantages. It goes very fast. There is no developer, there is no analyst, there is no testing. It's all the end user. The end user does everything him or herself. They plan, they develop, they test, and they know the requirements. And of course, by definition, the end user is very heavily involved because it's the end user who's doing everything. But there are some drawbacks in the sense that it's much more limited in possibilities. People sometimes they think they can do everything in Excel, but if it then needs to be scalable, mission critical, save, and so on, often there, of course, the story stops. And often these systems are also what's called like shadow IT, under the radar. Nobody knows that they exist except maybe from the person who has developed it or the team who is working in and so on. So the IT department is not aware of it. It's not screened for security. If your Office application, if the release of Office is certainly updated at a point of time by corporate ID, you get a new IT, you get a new version, and suddenly your scripts do not work anymore with that new version, you're on your own. You are expected to solve it. So it's very tricky. It lacks decent testing. We saw that example last time of the COVID analysis done by a certain government agency through means of Excel files. Well, you can do it when it's really urgent, when it's really needed. It's understandable, but of course it's very risky. It has not been formally tested. Certain procedures have not been applied. Security, as I said before, integration with other systems, all very, very difficult and risky. That leads us to the final consideration, and that also already refers to something that we hinted upon earlier. That's the actual success and the failure of projects. We already said that in 1994, Jim Johnson with his Standish Group, he performed that chaos report, studying the percentages of successful projects and the reasons of successful IT projects. And you might still remember from that lecture that we said, well, actually the percentage of successful projects is very limited. Most of them are canceled. Or not most of them, but a significant portion of them are canceled. A lot of them have overruns in budget and so on. And we said, well, there are a lot of failing factors. There are a lot of success factors that were listed. What was the thing here to recall? What was the remarkable thing that we said was so striking? If you look at those success and failure factors, sorry. Yeah, indeed. Only one of them is technical. Most of them are management related. So this planning, this analysis, this testing, where future managers are involved, this is super crucial. And those elements which are non-technical, making sure the requirements are okay, making sure that the involvement is there, making sure that there's executive support, those are crucial. We see that fact that there's an importance for management and not only technical people. We see that both in the project failure factors and in the critical success factors. The same reasoning holds there. But I know that some of you really had the very relevant question, but be careful. These are results from 1994. How is it happening now? Well, Jim Johnson, he went on retirement, so we will probably not get any very recent updates anymore. But the last time that he did the study was in 2020, and he mapped those differences. And what you see is that there is a little bit of hope. You see that the green part, it has increased a little bit. It went from 16 to 35, so kind of like almost double, so that's not too bad. But still, I mean, if you would tell to management, we will execute a project and the chances of your project to become successful is 35%, most of them will not smile. Most of them will not be happy. So it has improved, but it's still rather worrying. And we see the challenge projects, so the ones that are not okay on one of the aspects of being in time, in quality, within budget, roughly the same, and we see that, okay, the completely failed ones, they have decreased a bit. So the nuance story there is that, first of all, there is a little bit of improvement throughout time. It's still worrying, it's still a little bit depressing, but it has at least a bit improved. And second of all, of course, you need to make sure that there is the definition of the Standish Group of a successful project, which is within time, within budget, within specifications, which might be a bit strict. So these numbers might still be a bit extreme in the sense that their definition is also very stringent, very strict. What's also interesting is that in the 2020 report, Jim Johnson asked himself, would there be any kind of difference depending on the approach that you take? You have the waterfall approach, which we just saw, this sequential way of working, and you have the agile one. And based on the database that he created, he said, well, if we compare both of them, there is quite a difference, where we see that if you look at the successful ones, there is a significant increase in successful projects when you go from waterfall to agile. And there's a significant decrease in the failed ones. Both still have a very large portion which is challenged. But nevertheless, this is also an interesting insight. And of course, we need to be careful with interpretation because the study was done over a lot of different sectors and a lot of different companies and a lot of different people. So the conclusion here should not be you should always go for agile, but it is something to take into the back of your head that overall, over all these types of projects and countries and types of projects and organizations and so on, it tends to be a little bit more successful when you go for agile. Yeah. So those nuances I've just said. There's one thing that I need to mention here. If you want to do good project management, okay, maybe if you overrun your budget a little bit, that's not a complete failure. So those conclusions from the standard group, take them with a pinch of salt. But also, what's very important is that you need to be aware that there is this thing called project escalation. You need to be careful for that you don't keep on investing in a project which is clearly failing, which is going into the wrong direction. It's basically what we said in the beginning, that business case needs to have a continuous attention, needs to be a continuous endeavor. Well, if you're going through a project and you see it's failing or it's not going as you would like to go, then it's important to make sure that it does not just escalate and that you have the courage to reconsider it and to tell us, well, should we still continue? Should we still keep on investing money? And as I said before, this is a well-known concept and idea within management accounting, investment decision, and economics. Costs that you've made in the past, you should not take them into account for future decisions. A lot of people do it, but it's very irrational to do so. How to be more successful? Well, first of all, know the pros and the cons of the different project management methodologies, of all the agile versions of waterfall, and think about what is necessary for your project. What would be best suitable for your project? Be aware of those best practices, the success factors, the failing factors. We have seen some from the standard group, but there are also many other authors who have produced best practices, so it's interesting to take a look at them. You need good people to execute whatever you want in your company, but also for IT projects, and certainly the project manager, he or she who is in charge of the operational running of the project, should be a very knowledgeable person, should be a person who has experience in running those projects because it's not straightforward and it's not easy. And as I said before, we saw some activities which are very much business dominated, management oriented, and we have some tasks which are much more technological, IT oriented. In a successful IT project, both worlds need to meet. And so there needs to be a bridge, there needs to be an effort to bridge that gap, and a successful project needs to pay sufficient attention to that. Voila. The reading material that I've provided, so the paper that's attached to this section, is also something on this project escalation, being able to, or being courageous enough to say, well, we are not going to turn this project into a black hole, we're going to reevaluate it. So it's an interesting read. It's to be known for the exam. There are reflection questions on the platform, but we will not discuss it here in class. So I've also included some optional reading material if you want, but for the rest, I would like to close it here for today. Thanks a lot for your attention.